My name is Didem, and I'm a PhD student at Concordia University, working under supervision of Dr. Jeremy Clark. And today I will talk about our research entitled Absentia, Submit and Go Secure Function Evaluation. Okay, so let's start with what verifiable computation is. Verifiable computation is used when you want to outsource your computation to a third party. And there can be like two separate reasons for that, which I will explain in a few seconds. And when you outsource your computation to a third party, of course, there is the question that whether the result you received is correct or not. So in order to achieve this, the client should perform a verification on the result he or she received. And this verification should be much easier than doing the computation itself. Otherwise, there is no point in outsourcing the computation and having this type of verifiable computation scheme. So there can be two motivations. One big motivation is that the outsourcing party does not have enough computation power. It may involve big data, very heavy computation, and for that reason, they may want to just outsource their computation to a third party. And the second one can be the fact that the computation may involve inputs from other parties too. So no one would be willing to give their own input to the other party just to do the computation. So while these being the two main motivations behind verifiable computation, we will be focusing on the second one, where the computation involves private and sensitive inputs from several parties in our work that's called Absentia. Okay, so let's talk about secure function evaluation from a very simple use case. Let's say Alice and Bob want to compare their salaries. They are earning a certain amount of money, and they want to learn who is earning more. So, of course, a very trivial solution would be just saying how much they earn, and they would eventually know who is richer. But the thing is that they want to keep their income to themselves, and it is a private information for both of the parties. So secure function evaluation is used in this case. The basic use case I explained is also known as Yaw's millionaire problem in cryptography. Okay, so this being a very simple use case, let's think about some real-life applications where we may need secure function evaluation. So let's consider there are like two medical research centers or hospitals or maybe genomic companies that is doing some type of tests on their patients. And in order to have a better treatment procedure, they may just want to compare patient data to offer their patients better treatments, because maybe some of the medical research centers have a similar patient and they already applied a certain treatment. But of course, patient data is very sensitive and it shouldn't be shared with the other medical research centers in clear text. Another use case can be where there's location data. So location data is, of course, again, considered as private data, because you looking at the location pattern, you can figure out whether a person visited a hospital, where he or she lives, where they work, and all those type of information can lead to much serious implications in the end. So why some service providers would like to compare location data? Maybe they are providing some service based on the patterns that they have during using their some type of services, or they may want to classify based on the similarity of their location data. So in order to do that, they again would like to utilize secure function evaluation so that neither party just discloses their private inputs to any of the other parties involved in this process. And one last example can be comparison of banking data. So maybe some banks would like to perform some arithmetic operations on their joint inputs so that they can offer better services to their customers. And of course, none of the banks would like to share their data with the other banks, as this is again private and sensitive to their customers, and they have to protect the privacy of the customers of this bank. Okay, so our system Absentia is a blockchain-based approach for secure function evaluation. So why are we using blockchain? The thing is that it would help us to decrease the overhead for the users. So as the name suggests, as submit and go, the function can be evaluated in the absence of the parties. And the result can be trusted with the public ledger property of blockchain. And the very important point is that users does not have to do perform the verification. Because in verifiable computation schemes, the clients are required to do the verification part, and this shouldn't be a burden on them. So for this purpose, specifically, we are using Ethereum because it will serve as a secure bulletin board for the secure function evaluation, where you can think like there is like a transcript of all the things happening in the procedure. And as the blockchains have the property of immutability and non-equivocation, we are again utilizing from these properties to make sure that the computation is done correctly. And it can provide a financial compensation to the participants that do this computation, and for the work they do, they can just be easily financially compensated. And verification of the function of the result can again be done using blockchain, Ethereum's blockchain. Okay, so before I explain some more details about our system, let's look over the steps and the properties of Absentia. So the computation happens in the absence of users, which means that neither party has to be online, or they don't have to be present during the computation. They can just leave their inputs to the system, and the rest is just handled in the absence of them. And it will be very helpful for them that they can just guarantee that the result is correct when they came back to the system and get their results. And it will be publicly verifiable, as we are using blockchain to record this type of transcript that we are having for this procedure. And also, we are keeping the user's data private by encrypting the user's input and the output that is returned to the system. And one of the main aims is that we would like to provide non-interactivity between the parties, which means that neither user just have to exchange some data among themselves or like among the other trustees that are involved in the computation. They can just leave their inputs, and everything is handled by the system. Okay, so let's look at in more detail how Absentia works. So how do we determine the parties? Let's say we call them trustees, and let's say we have only single trustee. Alice and Bob are our users who want to perform secure function evaluation on their joint input. They have it encrypted, and let's say if we have only one trustee, then this trustee would own a single key pair, and he or she can directly decrypt it. So there is no privacy in this scenario, in this very trivial scenario. That's why we are utilizing something called distributed key generation that involves several trustees. So n trustees just come together, and they share a public-private key pair by doing the distributed key generation. So this means that every trustee owns a part of the public-private key pair, and not a single of them can directly decrypt and learn the result. Okay, so for the sake of simplicity, I will just explain a table that is like a very basic AND gate, which is shown here. And in order to do this secure function evaluation, the function should be determined ahead of time, and all the possible solutions corresponding to the inputs of Alice and Bob should be put in a table ahead of the time. And this is called an AND gate in logic. And so after this table is created, the input values are encrypted to hide the results under the public key. Okay, now let's talk about encryption. We are using exponential LGML, which is the public key encryption scheme. It is also a homomorphic encryption scheme, which means that it allows you to do certain operations on encrypted data without decrypting them. So it allows you to add two encrypted values and multiply an encrypted value by a scalar value. So you don't have to decrypt and see the data to do these basic operations using exponential LGML. And it is pretty efficient to use in this scheme. And also it has the commutative decryption property. So what does this mean? In the previous slides, I explained that there are several trustees. So it doesn't matter which trustee goes first and decrypts the result. So in any order, they can do their share of decryption on the encrypted value. And in the end, as long as the required number of trustees are gathered, you can have the full decryption. Also related to this, it can tolerate a party leaving the protocol, which means that it has a threshold decryption property. So let's say if we have 10 trustees, we can say that 7 out of 10 of these trustees are enough to do the decryption, and they can go in any order to obtain the plaintext value. Okay, so when these steps are done, we have to do re-randomization and shuffling. So re-randomization means that you change how the ciphertext looks. So it means that you don't change the underlying plaintext value, but the ciphertext changes by just maybe multiplying by 1, let's say. It won't change the underlying value, but the way the ciphertext looks changes. And after that, they should also shuffle the rows so that no one can just follow the inputs coming from Alice and Bob and learn the output too. We need to have another primitive at this point, which is called zero-knowledge proofs. So at a very high-level explanation, zero-knowledge proofs helps you to prove that you know a certain fact, a certain data, let's say, by not revealing what that value is. So at this step, each trustee has to prove that he or she has done this step correctly, like the re-randomization, to the other trustees by using zero-knowledge proof. So here we have non-interactive zero-knowledge proofs, which is a different type of a zero-knowledge proof, which means that, again, there is no interaction between the trustees, like exchanging data, and this also adds to efficiency of our system. Okay, so this step is called plaintext equality test. After doing all this all these steps, we are ready to do the plaintext equality test. So according to Pat, you just learn that whether two values are equal and nothing more. You can't know what is the underlying value of the ciphertext, but you'll just learn whether there is a match or not. So we have our table, encrypted, shuffled, re-randomized. And Alice and Bob comes with their inputs. In this case, Alice has encrypted 1 and Bob has encrypted 0. So plaintext equality test is performed to find the corresponding rows in their corresponding columns. As I told you, in this table, we just list every possible outcome of the computation. So just one by one, it would be compared. And in the end, the encrypted result, which would be 0 in this case, on the second row, and this result would be returned to the system. Again, as a summary, PAT involves re-randomization, partial decryption, and non-interactive zero-knowledge proofs to check whether the partial decryption is done correctly or not. Okay, so in conclusion, this is a work in progress towards a proof of concept using very basic use cases to show how our system can work. And in our setting, we have parties that have private inputs, and they want to perform a common function using their inputs. And it utilizes blockchain to decrease the burden of the users that they have to handle. And the submit and go property just enables them to leave their inputs to the system, and the steps that I explained can just happen in the absence of them. And which means that they don't have to be present at the same time and can have to be online at the same time to obtain their outputs of their joint functions. So this concludes my presentation, and I would like to thank you so much.